Hello. Okay, today's lesson is on combinatorics again. So this time we'll be learning about games. Right, so firstly, you guys can read what a game is. Just roughly. I mean, you don't have to like memorize this stuff. I'll show some examples of problems that are games soon. Yep, I posted the Jamboard in the chat if you want to join. You don't have to join if you because I'll be sharing the screen, but your choice. Okay, so hopefully you guys have had a read the slide. Um, I don't think this is like it's not something you should like memorize or something. I mean, I've never heard of this before, so okay, wait, sorry, I found out the link because it doesn't work. Okay, but anyways, for combinatorial games, right, it's just like something you should roughly understand, right? Like for example, the fourth point, the moves known to the other players. Normally, problems don't specify that, but you should assume that that's true. Um, okay, this link should work. Sorry. Okay, so we'll move on to the next slide. Here's the problem to introduce today's concept. That should be very simple, but it's not a trick question. I guess you can kind of imagine this as a game, but Bob is playing by himself, which is kind of sad. Maybe he's playing with the machine. Okay, hopefully that's enough time. This problem is very easy, but it is the main topic that we're focusing on today. Okay, so Bob starts with 7 balls, 7 red and 9 green balls, so he has 16 balls in total. And the machine does not change the number of balls he has. So if we consider the number of balls he has, he starts with 16, and that quantity will never change. But for him to have 17 red balls, he has to have 17 balls in total. So that doesn't make sense. Right, so what we did is we found a quantity that never changes, which in maths we call an invariant. And then we use that to show that something is unattainable. Because if that quantity never changes, but you need it to change to get somewhere, then you can't get to that place because it can't change. All right, so here's what an invariant is. Some problems for you guys to try. Problem two is probably easier, so maybe try that first. Again, in problem one, we want to prove if something is possible or not. Normally, if something is to prove something is impossible, you can use invariance. That's one of the most common ways, probably, that I can think of. Obviously, invariants don't work to prove that something is possible because it just doesn't work. Okay, hopefully that's enough time to do problem one, so I'll present that. Um, okay, so for the first problem, we have 1, 2, 3 up to 100, and we can select two numbers and replace them with the sum. Yeah, I'm drawing with my mouse again today. So, right, we have this. Okay, so for example, this would be a move. We can select 3 and 7, and then replace it with 10. Right, so hopefully you guys notice that the sum of the elements is the same, right? Okay, so let's say let f of n denote the sum of the you guys don't have to write it like this. This is a bit weird to like use f of n and stuff. I think this is how formal people do it though. So I want to be cool. But yeah, this is not necessary. And then yeah, okay, I'll stop trying to write it formally. So f of n is always equal to 1 plus 2 plus 100, right? Because after we select A and B and turn it into A plus B, the sum of the elements on the left is A plus B, which is the sum of the element on the right. Therefore, it's always equal to this. And if you guys don't know how to sum consecutive numbers, then that's an issue. Okay, but like to do it, you can pair them up. So we got 1 plus 100 plus 2 plus 99 plus all the way up to E plus 51. And that's 101 times 50. This idea of using symmetry is quite important, by the way. Very educational. So you guys can have a bit more time. Try problem one. This problem isn't that easy. Um, yeah. Um, the hint is maybe like draw out all of the possibilities. So like after 1 minute, the only possibility is one person, and then after 2 minutes, two people. But then after 3 minutes, we can have zero or three people. So then after 4 minutes, we can have zero or one or four. Actually, no, one or four, not zero or one or four. But yeah, yeah. When you do problems, always try to like just get as much information as you can. Obviously, we're not going to draw out 3 to the 1099 minutes. Okay, hopefully that's enough time. So after 0 minutes, right, we got 0 people. That's the only possibility. After 1 minute, we can't have 2 people leave if there's 0 people. So the only possibility is 1 person. After 2 minutes, 2 people. And after 3 minutes, we can have either 3 or 0, right? Because either 1 enters or 2 leaves. After 4, we can have 4 or 1 or 1. So these two are the same. And then after 5, we can have 5, 2, 2, 0. And we can have 6, 3, 1. No, 0. Right, and then this is also 3, and then, yeah. Wait, hold, okay. We cannot have 0 here. And then after 7 minutes, we can have 7 or 4 or 1. Okay, I can't really fit more. We will try. After 8 minutes, we can have 8, 5, 2. And after 9 minutes, we can have 9, 6, 3, and 0. And after 10, we can have 10, 7, 4, and 1. And after 11, we can have, okay, oh, it's a bit boring, but like I promise, this is going to be very helpful. All right, hopefully you guys see a pattern. If I was doing this problem, I'll just keep going until I see the pattern. I mean, obviously I would stop if I take like half an hour doing this, but hopefully eventually you guys notice a pattern, right? These are all multiples of 3. We think something is special about 3. And then if we look back, all of these have the same remainder after division by 3, right? Or the difference is a multiple of 3. This is true for all of them. Okay, so obviously we haven't proven this yet, but that's okay, so this is how I would approach the problem if I was you guys. So after 0 minutes, we can have 0, then 1, then 2. We can have 0, then 1, then 2, then 0, then 1, then 2. So that probably means after 3, okay, that does mean after 3 to the 199 minutes, we can have 2. Right, because it repeats in 3s, and this is a multiple of 3, so we can have 2 people in the room. And therefore, by our hypothesis, which we haven't proven yet, but is just an investigation, we can probably have all of these possible amount of people in the room. But we want 3 to the... Okay, that's my bad. After 3 to the 199, we can have 0, not 2. Okay, so we can have this possible amount of people in the room. And we want 3 to the 1000 is 2. This doesn't fit pattern. So if we can just prove that all of the possible numbers of people have the same remainder after division by 3, and we're done. And the way to prove that is not that hard. Okay, so now we know something is special about 3, right? There's a lot of 3s. We have 3 to the 199 minutes, and we have 3 to the 1000 plus 2. So we're looking for 3s. And then we notice every minute either we get +1 people or -2 people. And the difference here, 1 minus -2, so we found another 3. This is probably special, right? So, to properly prove this, I guess you could use induction, but intuitively, after n minutes, we have 3a plus b people, where b is the remainder, so like 3a plus 1 or 2 or 0. Then the possible amount of people we can have are 3a plus 1 plus b, or 3a minus 2 plus b. And these two have the same difference. I mean, the difference is a multiple of 3. The difference is 3, but it is also a multiple of 3. Okay, so then to inductively prove this, suppose after n moves, all of the possible numbers have the same remainder after division by 3. In the next move, also all of the possible numbers have the same remainder after division by 3. So, yep. Actually, the remainder is a pattern, right? 0, 1, 2, 0, 1, 2, which is also provable. Okay, so we'll go to the next problem. Okay, so, right, and that past problem, problem 1, we considered, which was the second problem we did, we considered what the remainder of the invariant was. Actually, no, not the invariant was the remainder after division by 3. So invariants often include the remainders of a number after division by 3. And right, last time in that problem, we considered the remainder after division by 3. But the most common one is parity, which means odd or even. And that's the remainder after division by 2. Right, there's a lot of invariants about parity. For example, we have 2 down there. An even number, the parity of an even number under multiplication is invariant because it's always even. That's quite useful. And then the parity of any number is invariant under addition with an even number, right? An odd plus an even is still odd, and an even plus an even is still even. All right, there's more, right? For example, if you sum an odd amount of odd numbers, then it's odd, which can be used as well. So here are some problems. Yeah, just do those two. This time you guys can probably do it in order. Okay, we actually have a student who is really enthusiastic to present their solution to problem 1 on the last slide. Okay, never mind, he doesn't want to present anymore. That's a bit tragic. Okay, for problem 1, right, there's different points of views. Again, this is a very common idea in problems, right? You can look at a problem from different angles. So far, for example, the a plus b problem, right, 1 to 100, and then we can rub them out. We considered all of the numbers in total, right? We didn't look at numbers individually. For this problem, we also have a similar idea, right? Maybe you guys were looking at the players individually, which isn't that helpful. Instead, try and looking at them all together, right? Also, another thing that you should have noticed about 127, it's probably true that that number is completely useless. However, 2 things that are maybe useful about it. that I would think of is firstly it's odd, and secondly it's 128 minus 1, where 128 is 2 to the 7. Also, it's quite big. So, but yeah, other than that, there shouldn't be anything special about 127. Okay, as someone asked what type of competition problem one is, it's just the people play each other. There's nothing special. It's not like elimination or something. They just play each other. They could play multiple times. They just play randomly. Okay, so I'll begin presenting the solution for problem one. Okay, so we have 127 players and they play games. Okay, so you should probably like a number to to the amount of games that the players play. And okay, so we'll say the first player plays A1 games, the second player plays A2 games, and up to the 127th player. Okay, and we want to prove that number who have played an odd number games is even. Maybe this reminds you of something that I said in the last slide, which is if we sum numbers, then if there's an odd amount of odd numbers, the sum is odd. In this case, we want there to be an even amount of odd numbers. And then what that says about sum, right? If there's an even amount of odd numbers in here, then all of the others are even, and then that means A1 plus A2 plus A127 is even. Right, we're working backwards right now, so this isn't a proper proof, but we're just getting ideas. Another way to think about it is if we have X games, A1 plus A2 plus A127 is equal to 2X. Because every time we play a game, right, let's say the game's between player I and player J, and therefore AI and AJ both increased by 1. Right, so every game increases the total by 2 because it increases the total of 2 players by 1. And therefore, we're already done because the sum is equal to 2x, which is even. And if it's even, then there must be an even number of odd numbers, because if there was an odd number of odd numbers, then the sum is odd. Okay, for problem 2, Jackie, if you want to present, you can present on slide 5.
Okay. Well, for the question, yeah. So for the end product to be like even, there has to be like a difference between two numbers, which is even. Well, if like n is even, say it was like 6 or something. Oh, the pen isn't working. Oh well. Well, if that was even, say if it was 6, then you can like pair up the odd numbers with the even numbers so that the difference will be odd. And then when you multiply all of them together, the product would be odd. But if n is odd, then there's more odd numbers than even numbers. So there has to be two odd numbers or more odd numbers paired together to form like an even number. So then the product altogether will be even.
Yep, that works. Okay, so the important thing we utilized was for that big product, right, for this whole thing to be even. As long as a single thing in here is even, then this is even, because an even number is invariant under multiplication. Okay, so we just want one of these to be even. And yeah, then the rest of Jackie's proof works, right? That was a good solution. So to reiterate, for example, when n is odd, if we have n equals 5, you got a1, a2, a3, a4, a5, 1, 2, 3, 4, 5. And we want this to be even, so we want just any one of these to be even. So if we consider a... Okay, no. We just want one of these to be even. So we want the 1 to be paired with an even number, then therefore even minus odd is odd. So this has to be paired with an even number. And then a2 has to be paired with an odd number. And then a3 has to be even, odd, even. But there's 3 evens and only 2 evens that we can pair them up with. So it is impossible to pair them up like that. So therefore, the product must be even. Okay, so just then we considered parity, which is the remainder after division by 2. But obviously we can divide by any number. Right, for example, in that problem we did at the start, it was division by 3. And in this case, we have another problem where we utilize an invariant. Alright, to use invariants, you just create one yourself and then prove that it exists and that it works. So you guys can have a go at this problem. Okay, you guys gonna have one more minute? Again, you guys can maybe try drawing that tree thing that I did for that other problem, where it was the room and people enter and exit. And then maybe you guys see a pattern. Okay, so problem, I could remind you of that problem where people were entering and exiting rooms. Because we got some plus ones and some minus twos, right? Very similar. So also we should think about three, right? The difference. So if we want, we can try figure out what happens and see if we can see any patterns. Okay, so firstly, if these two collide, then we get 9, 10, 1, 1, 3. If these two collide, then we get 12, 10, 1, 1, 0. And then if these two collide, we get 9, 13, 1, 1, 0. Um, yeah, you gotta be like genius or something to see something. Maybe we can keep going, but it's quite difficult to deal with. Alright, do a few more. Maybe one of you guys see a pattern like this. But it seems pretty useless. However, this type of problem, firstly, I feel like you should think that it is impossible. Because if it is possible, then you can just find a solution, right? It won't be that hard to find a solution. And then just like say what you did, like what order the bubbles collided in. Okay, so it's our hypothesis is that it's impossible, and now we're trying to aim for that. So maybe consider invariance because that is normally how you prove something impossible. Also, since the bubbles, there's nothing unique about the bubbles, right? Like to collide and create two of the other bubble. That's the same for any two bubbles. So they're symmetric. And if they're symmetric, when you see symmetry in a problem, normally the ideas are to like either consider like an anchor. Okay, so maybe we'll focus on one of them if they're symmetrical, or we'll consider the whole thing as a whole. In this case, we'll consider the whole thing. So using the idea from last time, when people were entering and exiting rooms, we'll consider the differences. Okay, so we got 10, 11, and 111. The difference between 10 and 11, and that's 1. The difference between 11 and 111, that's 100. And the difference between 111 and 10 is 101. If we look at other ones, we got 2, 100, and 99. I mean, no, 98. Okay, this is the same. And that's because those two were the two that collided. So they're the same. And then this went from 1 to 2, and this one went from 101 to 98. So if we want to look for differences of threes, that kind of doesn't work, but we'll keep trying, right? We wanna be optimistic here. We consider this, we got 497 and 101. Again, this one's the same. This one's 3 less, and this one's 3 more. So in this case, the differences actually are still 3, which is looking good. This one we got 103, and 10114, and 104. Again, this one follows it. All of the differences are multiples of 3. 106, and 107. Again, all differences are multiples of 3. So we feel like it should work, except for this case, right? This case it didn't work, so something weird happened. Maybe you notice that 1 plus 2 is 3, and that helps you see it. The thing you might notice is in this case, it went from increasing, right? 10 increases to 11 to decreasing, 12 and 10. And obviously that's going to flip the difference. Maybe instead of considering the difference, like the absolute value difference, we just consider the subtraction. So in this case, it would be 10 minus 12, which is negative 2. And that the difference between negative 2 and 1 is a multiple of 3. Okay, so I should prototype this. Let let the number of bubble be x, y, z, respectively. Okay. Then consider y minus x, z minus y, and x minus z. X and y collide. Y minus x is constant. Z minus y increases by 3, and x minus z decreases by 3. And if y and z collide, it's very similar, and if z and x collide, it's very similar. So therefore, we've proven that the difference will always change by a multiple of 3. However, if we consider 0, 0, and 1, 3, 2, which is what we want to get, right? We want only one type of bubble, and since the total number of bubbles remain constant, which is very easy to prove, there's 132 bubbles in total, so we'll have 0, 0, and 132. However, if we consider a difference, let's say between 0 and 0, the first and second terms, the difference is 0. But at the start, we had 10, 11, and 111. So therefore, the differences are 1, 100, and 101. None of these are multiples of 3, but 0 minus 0 is a multiple of 3. So that's impossible to achieve because all of these differences will only change by multiples of 3. So we'll go on to the next problem. So far we've seen invariance between like just numbers, sum of numbers. We've also seen invariance between the remainders of numbers after division. This time we'll consider invariance created by colors. Nothing special about colors, it's more just labeling things with colors. So you could label them with like A, B, C, D instead of colors, but normally people use colors. Okay, so I'll present the solution. All right, we want an invariant, and we remove two opposite corners, right? Color that in red. These two are gone. And the hint here in this problem is to, yeah, thank you, is to actually use the chessboard, right? The problem uses the chessboard. Maybe you thought that was irrelevant. It was just an 8x8 grid, but chessboard is actually kind of useful if we consider the chessboard color scheme. Hopefully this is enough for you guys to imagine the rest of the chessboard. So this gives us 32 black and 32 white. If we consider the two that we remove, they're both white. Oh, that depends on how we colored it, right? If we swap the black and white, then they're both black. But the important thing is both of these are the same color. Therefore, for example, in this case, now we have T whites instead. And if we consider placing dominoes, I mean 2x1 rectangles. Okay, for example, we do this. Hopefully, you notice that they always cover one of each color. Therefore, after every rectangle, you decrease the count by 1. So therefore, eventually we get the 2 blacks and 0 whites. So we can't get the 0 blacks and 0 whites. Thinking of coloring the squares is a bit weird. I mean, obviously coloring, again, it's very important to know that there's nothing special about colors, right? Instead, we could have like labeled them. We could have considered square 0, 0 and 0, 2 and 0, 4 and so on, and 2, 0, 2, 2, 2. But right, for like 0, 0, 0, 2, 0, 4, 2, 0, 2, 2, 2, 4. But coloring makes it quite neat to deal with. And to think of this, I guess, personally, it's important to know that a rectangle covers two adjacent grids. And maybe if we color it such that two adjacent grids are always different, that's useful. And colors are very common. It's very common invariant, so think of them, especially when you see grids. Problems with grids are actually quite common. Okay, next problem. So, alright, this is similar to what we just did. Show that you can not cover a 10 by 10 chessboard with 4 by 1 rectangles. Okay, for 2 minutes, because there's still quite a bit more we have to get through. Okay, I'll start presenting. Okay, so immediately this problem should be extremely similar to the last problem. By the way, one of you guys have been complaining about my handwriting a lot, so yeah, I actually upped my game. This is hand drawn. Okay. So the last problem we used chessboard coloring, right? And then we found an invariant that proves what we wanted. Also, again, when you see this problem, you should immediately think it's impossible, because if it's possible, the solution would just be a 10 by 10 grid with a bunch of dominoes on it to prove that it's possible. And that's kind of easy, right? I mean, you could try find it if you want to. It's not possible, by the way, but you could like try and look for a solution where you tile it. Also, something you might have thought of is the number of grids isn't divisible by 4, then obviously it can't be tiled. But it is divisible by 4, so like, don't try that. Okay, if we color it like this, by one rectangle does cover an equal amount of each. However, the problem now is there's 50 blacks and 50 whites. So if we cover 2 of each, it is certainly possible that we could go to 0 and 0. Instead, maybe we consider... Oh, this is difficult. Okay. So, maybe we try different coloring. Ignore the stuff on the left. Maybe we try coloring it like this. Oops. Right. In the same way, every 4x4 domino will cover exactly 2 of each color. However, again, if we finish the coloring and count it, there's still 50 blacks and 50 whites. So if we remove 2 of each, that doesn't do much. Okay, so now we try some other colorings. Maybe we think back to similar problems that we know. That's a very common technique. Right, the 8 by 8 chessboard with the 2 corners removed. Something else that was special about that solution was every 2 by 1 rectangle covered 1 of each color. Maybe we think about using 4 colors that each rectangle covers 1. So, right, if we do that, then this rectangle does cover 1 of each color. If we draw in this one, then we want it to cover 1 of each. So we make that one blue. And then if you continue the pattern, if you keep going 1 by 1, then you find that's what the first row has to be. There's no real way to know what the other rows should be. But maybe we try doing something similar to the chessboard, right? We create some diagonals. And this does work. Every 4 by 1 rectangle covers exactly 1 of each color, which you can prove. Make sure you prove it properly, by the way. Don't just draw some grids and rectangles. I mean, that could be a proper proof, but don't just say this to them like, oh. Okay. So now that we've found the coloring, such that every color is occupied exactly once by a 4 by 1 rectangle, we try counting the total number of each color. So let's say this is blue. We got 1, 2, 3, 1, 2, 3, then 1, 2, 1, 2, 1, 2. And if you continue it in total, never mind, this is 3. Oh crap, what did I do? Okay, but consider the total. If we counted it properly and then counted it, we get 28 blue. And greens, we get 1, 2, 3, 1, 2, 1, 2, 1, 2, 3, and 1, 2, 3. Okay, hold on, what am I doing? 1, 2, okay, we got 10 in the first 4, and then another 10, and then we got 5, so 25 greens. Already when we got 20, wait, hold on. 1, 2, 3, okay, we got 10, 26 blues, that's my bad. Way to count it is that it repeats every 4 rows. Right, this row is the same as this row. We count in groups of 4s, and we got 10 blues in every 4. So 10, 20, 26. Already, since there's 26 blues, we kind of know we can't have an equal amount of every color, because if we have an equal amount, that would be 25 of each. So we're done, right? Because every color decreases by 1 at a time, so we can't decrease them all to 0. Next problem. It is already 9 o'clock. If you guys have to leave, then okay. Hopefully I'll finish in 10 minutes. Sorry. Okay, so now we'll move on to another type of invariant. This one isn't really related to any of the others. Actually, it's kind of related, I guess, to the 1, 2, 3 up to 100, I guess, because you're just creating a number. Okay, hopefully that's enough time. So again, I've hand drawn another grid. Yeah, so we have pawns in these rows. Most of you are saying no. All right, so when you see this problem, probably try it yourself. Maybe we see something. Maybe it is possible, right? Maybe we find the solution. If 2 pawns are in adjacent squares of the same row. Okay, so for example, we can remove these 2 and then put 1 there. And then remove these 2 and put 1 there. Immediately, we should notice that the columns don't really matter, right? Like these pawns could go anywhere. And we could pick 2 pawns from any 2 columns. Never mind, they have to be together. Okay, but like we can move it. Yeah, we can move it to anywhere. It just as the row above. The columns don't really matter. Okay. And then we got those 4. So then we can create 2. And we got those 2. And we can create 1. Alright, similarly, we can remove these 8 and create 1 in the next row. And then we can remove these and create 1 in the next row. And then remove these and create 1 in this row. But now we're kind of stuck. We can't do much. And to do this, we find another invariant. That's called the invariant f of x again. All right, so in the starting position, okay, we want to assign values, these probably to the rows, like to the pawns in the rows, because the columns aren't that special. So we want to give each pawn and each column and each row a value. And then if that value is too low, and if that value doesn't change, then maybe we can prove that we can't have one in this row. So since we can take two in one row and then create one in the next row, maybe we should give them doubling values, right? So if this is 1, 2, 4, and then 1/2, 1/4, 1/8. Okay, that's the wrong way around. Um, okay, so we give this 1, 2, 3, 4, 5, 6, 7. Okay, I can't count, that's my bad. Okay, but like hopefully you guys get the idea. We give them doubling values. And this way, every time we make a move, we take two in one row and then create one in the next row. So our total value is same. It doesn't change. Hopefully you guys see that. Now, what is this value at the start? We have 8 in this row, 8 in this row, 8 in this row, 8 in this row. So 8 times 8 plus 8 times 4 plus 8 times 2 plus 8, which is equal to 120. And then we want a pawn in this row, which is 128. And that's higher than 120. So we're done, as long as we prove that this quantity cannot increase. Okay? Indeed, it cannot increase. It can't even change at all. It can't decrease either, because we take two and put one in the next. You could think of this as giving these values, right? Maybe these are worth $1, $2, $3, $8. I don't see how that's that helpful though, but like maybe I've seen people say that. So I don't know. Okay. Now, okay, so previously we were learning about invariants, which are things that don't change. And now we will learn about monovariants, which are things that only change in one direction, or they could not change, okay? So for example, in that case, when we gave the value of the pawns 120, maybe it's 120, and then after one move, it's 119, and then 118, and then it could still be 118. It's still a monovariant. A monovariant is defined as something that only, if it changes, it only changes in one direction. So we could say the same. As an example, using monovariants. Okay, hold on, this is an invariant. Oh wait, yeah, I couldn't find any good problems. Okay, that's my bad, guys. We can try this problem. Actually, I'll see if I can find one right now. But in the meanwhile, try that problem. Okay, it is almost 9:10 now, which is when I promised to stop. So yeah, let me know if you want to go. I'll try find a good problem. Um, okay, I'll present the solution to this problem, and then I did find a problem using monovariants, which will hopefully be educational. Okay. So in this case, we got 1, 2, 3 up to 100, and we can remove two numbers and swap them with a plus 1 times b plus 1. So that would be 3 times 4, which is 12. And we want to prove whether final number will be different depending on what we do. So firstly, I guess we can do some investigation. If we just select these two, and then the next 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 two, we'll get 1 plus 1 times 2 plus 1 plus, okay, never mind, we can't do this. Okay, this is the first time I've tried this problem. So we're seeing how you approach problems. It's very educational. But yeah, this is kind of useless. Unless if you make the important observation already. Yeah, so we can't really see what we would get. So we look at the problem again and look at the conditions. And AB plus A plus B. Do we see anything special about this? So this is A plus 1. This is kind of symmetric, right? We got A plus B. A and B are added once, and we got A times B. So that's nice that it's symmetric. It's also equal to this. This is also symmetric, right? We got A plus 1 and B plus 1 multiplied together minus 1. And this is kind of nice. Okay, hold on. What am I doing? We got 1 plus 1. Okay, we got 1 times 2 plus 1 plus 2. And that's what we get if we select these two. If we select those two, then we actually get 2 times 3 plus 2 plus 3, which is 11, not 12. Yep, that's my bad. Maybe you notice 11 is 1 less than 12. And you get to this. And so we consider this. This is our invariant. We got a1 plus 1, a2 plus 1, a3 plus 1, all the way up to an plus 1, where those are the terms. Right at the start, we got 100 terms, and the quantity is equal to 2 times 3 times up to 101. And every time we make a move, this quantity is invariant, right? Because we go from a plus 1 times a2 plus 1 to a plus 1 times a2 plus 1 minus 1, and then plus 1. So it's still a plus 1 times b plus 1. It's invariant. And now for a problem that I found using monovariants. See if I can share it. Okay, that's the problem. And since some of you might need to go, maybe it's your bedtime, it's a bit late, and I'll just show you how I approach this. I've never done this. Actually, I might have done this problem before, but I don't remember doing it, so might as well never done it. Okay, we got a unit fraction. This is the definition of a unit fraction. This is the definition of a unit fraction. And we want to prove every rational number between 0 and 1, so a over b, where a is bigger than 0, but less than b. Actually doesn't say whether it's inclusive or not. If it's 0 or 1. Okay, prove that every rational can be expressed as a sum of finitely many distinct unit fractions. So if it's 0, if it includes 0, then yeah, 0 is equal to 0, and 0 unit fractions. So there's a finite amount of unit fractions. 1 is equal to 1 over 1. This is 1 unit fraction, which is also a finite amount. It doesn't really matter if this is inclusive or not. Now we just have to consider a over b, where a is bigger than 0 and less than b. Obviously, a and b are natural numbers or positive integers, whatever you want to call it. So, for example, let's consider this rational, 5 over 6. We want to express that as unit fractions. So first, the intuition would be to add the biggest unit fraction. The biggest unit fraction less than this is 1 over 2. And that's 1 over 2 plus 2 over 6, which is equal to 1 over 2 plus 1 over 3. So we're done already, right? We got 2 unit fractions. They also have to be distinct, which I didn't notice, but these are distinct, so that's fine. Let's consider another fraction, right? 7 over 9, that's equal to 1 over 2 plus 5 over 18, which is equal to 1 over 2 plus 1 over 4 plus 1 over 36. And we're done again. So we keep adding a half, right, which is the biggest unit fraction, that's still smaller. Then we got 5 over 18th, which is, so then we add the biggest unit fraction, which is smaller than that, which is a quarter. And then we subtract that, and then it's 1 over 36, which is already a unit fraction. Maybe you think about doing induction, but that doesn't really work because they are infinite. Okay, well, normally we use induction for infinites as well, but you got to prove it for infinite numerators and then infinite denominators, like infinity squared, which I guess still works, right? Like, for example, normally in induction you go from 1 to 2 to 3 to 4 up to infinity. You can also go from 0, like if we consider the grid, right? You can prove it. We can induct this way, and then we induct this way. But maybe we just go with what we've been doing, right? We've been adding this unit fraction less than the fraction. So for example, again, 10 over 13, we add 1/2, and then that's 7 over 26, and then we add a quarter. So we got 14 over 1 over 52, I think. So we got some more unit fractions. So algorithm we've been using is adding the biggest unit fraction, which is less than the current fraction. Obviously, if we can do this, it will work because eventually it decreases enough. Okay. Actually doesn't work because the fractions could become infinitely small. Okay, but we'll continue with this for now. We know there will be distinct, which the problem wants, because if we subtract this unit fraction, what's left is less than, quite a bit less than this, because the unit fractions don't double, right? Each unit fraction is more than half of the previous unit fraction, but this will be less, because if this was more than this, then this would be more than double this. And we could just add the previous unit fraction. Okay. Wait, if I can't solve this, this is gonna be quite bad. I'll try my best. We know we can always decrease it at least. Yeah, but the issue is, it's because it keeps decreasing doesn't mean it will become zero, because it can become infinitely close to zero. There are infinite fractions that are very tiny. Okay, so we'll keep investigating. Maybe we have 13/7. Okay, no, we'll stop using things that are bigger than a half. 7/17. By the way, if you guys have to go, then go. I might take a bit long, so this is gonna be quite bad. Um, a third, and then okay. Yeah, so we know we can keep decreasing the remainder. Hmm. Okay, I'll keep trying. Eventually, since I should probably be teaching you guys, I'll look for the solution. I'm very sorry that I'm struggling this much. Hmm. Okay, sorry, I'm being rushed. Not rushed, but okay. I'll read the solution for you guys. I'm very sorry about this. Oh yeah, we can read it together. That's as much as I can do with you guys. I sincerely apologize for not being able to solve it. Oh, mm. That is my bad. I'm so sorry. Yep, okay, well, hopefully you guys understand what a monovariant is. That was a very bad example. I apologize. You guys can read it. If you guys don't understand it, then ask me, I guess. Not qualified after that, but okay, anyways, that's it for today's lesson. If you guys don't understand it, the numerator has to be finite. So since the numerator is always decreasing, this time it's a strict monovariant, right? The numerator won't stay the same. It's always going to decrease. So eventually it reaches zero because there's finite numbers under less than a finite number. Finite positive numbers less than a finite positive number. Okay, that's it for today's lesson. I'm very sorry, guys. That was very bad. But bye-bye. I am so sorry about that. That was my bad. I probably should have read the solution. Yep, yep. Thank you.